Next, we'll learn another method of finding a particular solution of the non-homogeneous second order linear ODE. This method can be used only when the right hand side of the non-homogeneous ODE has specific form like k e raised to rx, k x raised to n, k cos omega x, k sin omega x, k e raised to rx cos omega x, k e raised to rx sin omega x, k e raised to rx x raised to n, and so on. Here k, r, omega are constants. If the right hand side is one of this form, that is rx is one of these functions, then we take the particular solution to be of that form. Suppose the Rx is of the form 4 cos 5x, then we'll take the particular solution of the non-homogeneous ODE to be of similar type, namely some C1 cos omega x plus C2 sin omega x. And then we determine what is the value of C1 and C2 by substituting that particular solution in the non-homogeneous ODE and determining the value of C1 and C2 that satisfies the non-homogeneous ODE. But here is a remark. If it happens that the particular solution that we are taking, looking at the Rx, that particular solution also happens to be a solution of the associated homogeneous equation, then this method fails. So it says the method may fail if the choice yp happens to be the solution of the corresponding associated homogeneous equation. We'll consider this example, which we will like to solve using the method of undetermined coefficient. Find the general and a particular solution of the DE y double prime minus 3y prime minus 4y is equal to 3 e raised to 2x. So looking at the Rx, we should try to look for a solution which is of the form k e raised to 2x. That is, since the Rx is of e raised to 2x form, we will like to have the solution of this non-homogeneous ODE to be of the form k e raised to 2x, and when we substitute this in the given non-homogeneous ODE, from that we will find out what value of k satisfies this. So we start with an arbitrary constant as a candidate solution. So put y is equal to k e raised to 2x. We substitute y is equal to k e raised to 2x in this ODE as written here. So double derivative of this appears here. Double derivative will be 4k e raised to 2x. The single derivative of this quantity has to be substituted here. So when 2 will come down, so we'll have 6k e raised to 2x minus 4k e raised to 2x is equal to 3 e raised to 2x. So this term will cancel with this term, and so we solve this. So we'll get the k value to be minus half. So a particular solution of the non-homogeneous ODE is minus half e raised to 2x. How did you get this? We substituted k is equal to minus half in this y is equal to k e raised to 2x, and we got the particular solution. This is the method of undetermined coefficient. That coefficient k was not known and we tried to determine it by substituting it back. So undetermined coefficient method. So how to get the general solution? For that we have to find the general solution of the associated homogeneous ODE. So we have to look at the roots of the characteristic equation of the associated homogeneous ODE. That will be m square minus 3m minus 4 equal to 0, and from this we get the roots are 4 and minus 1. So the general solution of the associated homogeneous ODE is C1 e raised to 4x plus C2 e raised to minus x. So the general solution of the non-homogeneous ODE is y is equal to C1 e raised to 4x plus C2 e raised to minus x minus half e raised to 2x. We'll look at another example now. Find the general solution and a particular solution of the ordinary differential equation y double prime plus 5y prime plus 6y is equal to e raised to minus 3x. So for this, we'll search for a solution. Again, like previous case, the solution we will look to search for here should be of the form k e raised to minus 3x, where k is constant. I would like to determine k by this method of undetermined coefficient. So we take y is equal to k e raised to 3x and substitute it here. So we compute what happens. We take the double derivative here, the single derivative here, and compute this. It turns out that the left hand side will be 0, whereas the right hand side is not 0. So this does not give us any value of k. So in this case, the usual method of undetermined coefficient fails, because it happens that e raised to minus 3x is also a solution of the associated homogeneous equation. So we had made a comment there that if yp happens to be a solution of the associated homogeneous equation, then the method may fail. Y e raised to minus 3x is a solution of the associated homogeneous equation because for the associated homogeneous equation, minus 3 is the root of the auxiliary equation or the characteristic equation. So we multiply x with e raised to minus 3x to get a particular solution of the non-homogeneous ODE. So here ypx is taken to be kx e raised to minus 3x. If minus 3 would have been a double root of the auxiliary equation or the characteristic equation of the associated homogeneous equation, then we know that x e raised to minus 3x would have been also a solution of the homogeneous equation. So in that case, we had to choose yp is equal to k x square e raised to minus 3x as a particular solution. In this example, minus 3 is not a double root of the auxiliary equation, and hence yp x is equal to kx e raised to minus 3s would work. When we substitute ypx is equal to kx e raised to minus 3x in this non-homogeneous equation, now the left hand side will not be 0, and in fact we will be able to determine the value of k on substituting here. It turns out that k is equal to minus 1. You can do it yourself and check, and then you can write the general solution using this value of k. So here is summary of the undetermined coefficient method. If Rx, that is the right hand side, happens to be x raised to d e raised to ax, or even px e raised to ax, with px being polynomial of degree d, then the candidate solution is yx is equal to x raised to mu a qx e raised to ax. What I am saying is, if Rx happens to be x raised to some power, say d can be 4 or anything, and multiplied by e raised to ax, where a can be 2 or something. So Rx could have been x square e raised to 2x, or it could have been a polynomial times e raised to ax. Let's say polynomial was x square plus 2x plus 3, this polynomial multiplied to e raised to 2x, something like this. So polynomial can be of degree d. For example, what I just now told was a polynomial of degree 2. If this kind of Rx is there, then the candidate solution that we take and substitute in the non-homogeneous ODE, that candidate solution can be taken to be x raised to mu a, where what is mu a? Mu a is the number of times a occurs as a characteristic root, that is the root of the characteristic equation. So x mu a multiplied by qx multiplied by e raised to ax. This e raised to ax is same e raised to ax as which appeared in Rx, and this qx should be a polynomial of degree d. So here all these coefficients are undetermined coefficient. Ad plus ad minus 1 x plus dot 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 a naught xt is the qx, and ad minus 1 dot 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 a naught, they are all undetermined coefficient. On substitution we will be able to determine these coefficients. Similarly, if Rx happens to be xt e raised to ax cos bx, where b can be some number, let's say 3, or even if Rx happens to be px e raised to ax cos bx, where px is a polynomial of degree d, then the candidate solution that we have to take and substitute in the non-homogeneous ODE should be yx is equal to x raised to mu of a plus ib e raised to ax multiplied by bracket q1x cos bx plus q2x sin bx bracket close. Here mu a plus ib is number of times a plus ib occurs as a characteristic root. That means number of times a plus ib is a root of the characteristic polynomial. And see, if px is of degree d or xd occurs there, then we have to choose this q1x to be any polynomial of degree d, is arbitrary polynomial, and q2 to be arbitrary polynomial of degree d. And in that case, all this coefficient ad minus 1 up to a naught and bd minus 1 up to b naught, they are undetermined coefficient. On substituting yx in the non-homogeneous ODE, we will be able to find out the values of all these coefficients ad minus 1 up to a naught and bd minus 1 up to b naught.